And we are recording. Welcome to the evening of Python coding. Today, like every other evening of Python coding, we have a demo of some Python library. Zhanghui Jin, he's an engineer from Amazon, from the machine learning section there. He will explain exactly what he's doing there as much as he can in a second. He's going to talk about a machine learning library called MXNet. It's a foundation library for neural networks. This is more or less I can tell you about it. But Jean-Louis, and I believe he prefers Jin. So Jin, go ahead and tell us more about the MXNet.
Yeah, thanks. Yeah, thanks for so much for the introduction. Hello everyone, my name is Zhenhui Jing, and I'm a software engineer with Amazon AI. So today I'm really happy to be here and talking about MXNet, what MXNet is, and then I will show you some code about what you can do with MXNet. Yeah, I have prepared a series of notebooks on my GitHub. So I will give a short demo on the first three notebooks. So feel free to follow along with the notebooks if you are interested in them. Okay, yeah, let's get started. So for those who don't know what MXNet is, so it's an open source deep learning framework designed for both efficiency and flexibility, and also ready for production. Why do we use MXNet? Is because of a couple of shining features. It's fast and scalable. It has multiple language support, such as Python, Java. We do have scalar and other bindings. Of course, like most of the other deep learning frameworks, Python binding is the most popular and user-friendly one that has a bunch of user adoptions. Also, MXNet.
Jen, can you zoom
Yeah.
in just a little bit? Can you zoom in a little bit more on your screen, please?
Yeah, sure.
That should work, I think.
Yeah. That's good.
Thank you.
So, yeah, can you see my screen clearly?
Okay,
yeah.
We're
Okay,
good.
let's continue.
We're good,
Yeah.
Jin. Go ahead.
We're
Sorry
good.
for the interruption.
Yeah. Also, it's also backed by Apache Software Foundation and supported by AWS, Microsoft, and has an active open source community. It also supports a wide range of hardware and platforms. So basically, in MXNet, we will use the array to describe n-dimensional arrays with an arbitrary number of actors. So if you are familiar with NumPy, which is a fundamental package for scientific computing, then you must know the powerfulness of n-dimensional arrays. In MXNet, we provide the NumPy compatibility, which means we have a NumPy compatible array library that extends with additional features. So first, MXNum NP array supports fast execution on a range of hardware configurations, including CPU, GPU, and multi-GPU machines. Second, MXNet NP and the array executes code lazily. So
You will have to explain lazily for people who, some of our audience is beginners.
yeah, what's lazily here means it will um, be like parallelized operations across the different hardwares. So because in MXNet there is intermediate representations um, to mapping the operations into the graph. So all the ND arrays inputs can be compared into the graph and compute lazily. So that's what the lazily mean. And I think the third part is I should highlight here is MXNet also um, also uh, the ND array and the NP operators in MXNet are all standardized operators, which used to improve the interoperability with other array libraries. So the standard here refers to the Consortium for Python Data Array API standards. Yeah, this consortium aims to address the fragmentation problem in machine learning and deep learning frameworks, and will create the synergy by developing API standards for arrays and data frames. You will get familiar with these features in the next section. Yeah, and in MXNet we will use block to form different neural networks. A block can be a single layer component consisting of multiple layers, or the entire complex neural network. So one benefit of block abstraction is that you can recursively combine like blocks into large artifacts. So by defining the code to generate blocks or arbitrary complexity, you can write the compact code and implement complex neural networks. I think I will introduce these details in the third notebook. And also in MXNet, hybrid block is another abstraction to combine both symbolic programming and imperative programming. Imperative and symbolic programming represents two styles of deep learning programming interfaces. And I think most of the deep learning frameworks choose either imperative or symbolic programming.
Can you give a
So
simple
for
example of symbolic for people who are new to us? Some of our audience are really new. So I see
yeah,
some
sure.
code here. Can you go
Yeah,
over and explain?
I will elaborate imperative programming first. So for imperative programming, it's easier. So when imperative programming is used in Python, the majority of code is straightforward and easy to write. So look at the code here. Python is interpreted language. When you are evaluating the fancy function, it performs operations, making up the function body in sequence. That is, you evaluate e equals to add ab first, and store the results as a variable e, thereby changing the program state. The next two statements, f equal to add cd and g equal to add ef, will be executed similarly. So performing additions and storing the results as variables. So it's imperative programming. So although imperative programming is convenient, but it may be inefficient. So on one hand, even if the add function is repeatedly called throughout the fancy function, Python will execute the three function calls individually. if these are executed, say on a GPU or on a multi-GPU environments, the overhead arising from the Python interpreter can become overwhelming. Um, Moreover, it will need to save the variable values of E and F until all the statements in fancy function have been executed. This is because we do not know whether the variables E and F will be used by other parts of the program after statement E equal to AB, add AB and F equal to add CD are executed. But for symbolic programming, so
just to summarize imperative basically you're telling us whatever you see is executed the minute you ask it to do. And it creates a lot of operations because it has to run all those functions each time, correct?
Yes, exactly.
Okay.
Yeah.
And now symbolic is the kind of different. So let's go to symbolic.
Yeah. So for symbolic programming, the computation is usually performed only once the process has been fully defined. So it usually involves three steps, like defines the operations to be executed and compiles the operation into an executable program, then provide the required inputs and call the compiled program for execution. So this allows for significant amount of the optimization. So firstly, we can skip the Python interpreter in many cases, thus removing the performance bottleneck. And the second, you can see the code here. We turn the add and fancy function into strings, and then we compile them. A compiler might optimize and rewrite above code into print 1 plus 2 plus 3 plus 4, or even just print 10. This is possible because since the compiler gets to see the full code before turning it into machine instructions. So for instance, it can release some memory or just never allocate it for E or F, these intermediate variables. Or it can transform the code entirely into an equivalent piece. So
So you can see the entire computation before you actually perform it. So the machine knows, oh, I'm going to compute, let's say, 100 numbers, and I'm going to use additions, and then it can do it more efficiently. Correct?
Yes, exactly.
Okay, and this is where
Thanks for
lazily comes in, correct? Like the fact that you first define but nothing happens, and then sometime in the future this execution will happen when the computer has time. This is why it's called lazily. This is correct here?
Yes, it's the same mechanism behind the MXNet. So I will elaborate later.
Okay.
So when designing the MXNet, developers considered so whether it is possible to harness the benefits of both imperative and symbolic programming. Um, the developers believe that users should be able to develop and debug using pure imperative programming, while having the ability to convert most programs into symbolic programming. So now you can see hybrid block, hybrid sequential classes to experience hybrid programming, which will combine both imperative and symbolic coding experience in MXNet. So I will show some details in the third notebook. Now comes to Gluon. Gluon is imperative high-level front-end API in MXNet. So so it's flexible and easy to use, and it can provide everything you need from experimentation to developing the model without sacrificing training speed. And MXNet has a huge ecosystem based on Gluon frontend, including Gluon NLP, Gluon CV, and Gluon TS. I would strongly recommend to read dive into deep learning, which is an open source book, which will include a lot of deep learning knowledge with multi framework code. Yeah. Okay. I think we can move on to the next notebook.
Okay.
Yeah. Okay. So in MXNet, we bridge the gap between the traditional machine learning and deep learning through these NumPy APIs. So this section will introduce MXNet, NP, and NPX, these packages. On the NP side, MXNet extends the NumPy library with enhancement of automatic differentiation and GPU acceleration, and it's also compliant with Python array API standard. NPX package further extends it by providing operators that's not part of NumPy, which can also be called with neural network extension. So to get started, we need to first import NP and NPX package together from MXNet. Then in the next step, we will create a two-dimensional array, which is also called a matrix. This matrix has values from two sets of numbers, or we can call it a tuple of two tuples of integers. So let's run it. Yeah, you can also create a simple matrix. With 2 rows and 3 columns, and fill it with ones with np.full operator. Alternatively, we can use the following creation routine, like np.ones, which has the same operation that create a 2 times 3 matrix filled with ones. Yeah, you can also create arrays whose values are sampled randomly. So, for example, sampling values uniformly between -1 and 1. Right, let's try it.
So you're performing many operations. This is the NumPy, or is it the MXNet equivalent that you're using here?
It's MXNet NumPy equivalent arrays and operations.
Does it is it very compatible to NumPy, or is it like everything that NumPy can do, it can do, or does it overlap in some of the things? Is it a little bit different?
Yeah, as I introduced here in NumPy, this package from MXNet, it has all the NumPy compatible arrays and NumPy compatible operators in this package. I think we have covered about 600 or 500 operators in NumPy MXNet NP namespace, which has this equivalent functionality as these NumPy operators. But for those like neural network operators, we will include them in the NPX, which is the extension package. Yeah, I think I will show some examples later. Okay, let's move on. So for MS NumPy NP ND array, it has all the features and that official NumPy ND array has. So you can get the dimensions of each ND array by accessing the accessing shape attribute. You can also query for size, which equals to the product of the components of the shape. In addition, dtype tells the data type of the stored values. So you can specify the data type when you create an ND array. Like you can specify it's as int 8. And if you do not specify, the default will fall back to int 64 as the element to fill is a 1, which should be a 64-bit signed integer. So when we multiply, the output data type will be with the most precision. Okay, so here it's float 32. Also, MSI NP array supports a large number of standard mathematical operations. So for example, element-wise multiplication. And you can also perform exponentiation with NP, NP exp. And also you can perform a matrix by matrix product, which is also called a matrix multiplication.
Just I'm curious, Jen,
And
is this product a separate library that just implements the NumPy interface, or is it a wrapper around NumPy and it's actually running NumPy inside of it and then extending it?
It's not the wrapper around NumPy, but we implement all the operators and ND arrays in MSNet backend. Yeah, for all the operators in MXNet NP package, we have the including like CPU kernels, GPU kernels to accelerate on these hardwares.
Mm-hmm.
Yeah.
Okay, thank you.
And also like also we can perform some like ND array summation and gathering the mean value, and you can perform flatten and reshape. Yeah. So also the ND array supports slicing in many ways, just as what we can do in official NumPy library. So say we have a Y ND array, and we can read a particular element, which will return a one-dimensional array. And we can also read the second and third column from Y. And this example shows how to write a specific element. And you can also perform a multi-dimensional slicing like this. Yeah, Also, MXNet will provide a mechanism to convert MXNet ND arrays to and from the NumPy ND arrays. So you can use as NumPy to convert MXNet ND array to NumPy ND array, and use array function to convert back. So additionally, you can move all the ND arrays to different GPU devices. So for example, if you can copy to a specific GPU with ID 0, you can run this. Yeah, lastly, which should be highlighted here is we can also convert between MXNet ND arrays with other array libraries that follow the array API standard. For example, Pytorch Tensors. So let's import Torch and let's create 2 Pytorch Tensors. Yeah, one is created with tuple of tuple integers, specified data with flow 64, and the other is a 2 times 5 tensor filled with ones. So usually we will use DLPy API to convert between different array libraries. So here, DLPack is an in-memory tensor structure. So we can see here, it will enable data interchange with zero copy among different array packages. So let's convert Torch tensors into MXNet ND array. And then perform the matrix banish matrix product. We'll get like this. Okay, so based on these common interfaces, we can write like some common functions can apply to both MXNet, NumPy, ND arrays, and Pytorch tensors. So firstly, we need a function to get the namespace of the input arrays. We can generally use the array namespace, which is also part of the standard API specified, to simply return the namespace, which can be used later as for the calling an array API specific method. So we can see the common matrix multiply toy example. We can use this function to do matrix multiply on both MXNet and the arrays and Pytorch tensors. Yeah, I think this will demonstrate the feasibility and the power of using the array APIs in like our model building and some other tasks.
I assume you're using very small numbers here, so it's like you won't see the speed up, but yeah.
Yes. Mostly for the for the inter-memory change, we will require something like stream synchronization on like GPUs and do some memory copy, which will also introduce a lot of overhead. So here I just give a simple example on such a simple, small size of ND arrays.
Yeah. Yeah, you explained well. That's like this is the base for every computation that will happen later, and it's compatible with NumPy. These are important.
Yeah.
You're going to show the
Okay.
next network, maybe, but before this, it's actually before you move in, you're dropping some names, and I want those to be a little bit explained to the audience. So you're saying deep learning and traditional machine learning. So, in a nutshell, without going into details, can you just give the difference?
You mean the
No,
difference between?
yeah, when you say
Mhm.
deep learning, why is it not machine learning? What's the difference?
Yeah,
Typically,
uh from my perspective, I think deep learning is is just from its naming, like it's a deep. We will create really a lot of layers of
yes,
networks,
yes,
and we are
yes,
tuning these parameters on this uh, lot of layers.
yeah.
So I think in the next notebook, I will introduce the layer and the blocks, which
Okay,
is
let's
yeah.
go. But you explained deep learning. It's then when you have many layers that kind of like go deep, like because there are many, many layers on top of each other, you can go deep.
Yes, exactly. Okay, so let's move on to create such a neural network with MXNet, block, and hybrid block. Block and hybrid block is a part of the GLOM package, which is a simplified high-level programming package in MXNet. To use GLOM, we need to import like NP, NPX along with GLOM module.
So before you start with the neural network, can you kind of explain a little bit what a neural network is for people who never seen this before?
Yeah, sure. I think we can refer to some part of this book. Um,
Um,
so I
without,
think neural network. Hmm?
okay. So there's a book that explains multi-layer perceptrons, but here's a diagram.
Yeah, here is a diagram. So for neural network, I think it's like a lot of neurons are connected with each other, and we have different layers to abstract each input into the different features,
Okay.
and yeah, I think for those detailed introduction of the neural network or deep learning related knowledge, uh, I think we can refer to this book.
Okay, where do you find this book? So people can later go ahead and it's part
Yeah,
of the
sure.
MXNet. It's dive into deep learning. It's
Um,
online.
it's called Dive into Deep Learning. You can find this book online, or I can paste
I
the
already
book.
pasted the link to the book in the chat.
Okay, great. Thank you.
Perfect. Thank you. So
Yeah, thank you.
so this is for people, but about the deep learning, the network you showed had three layers there, correct? So in deep neural
Yes,
networks, we'll have sometimes more than three. And the more they are, the deeper we go. This is hence the name deep.
yes.
Yeah. And each layer
So
does
the
some very simple computations, but when you put them on top of each other, it becomes very complex function that is being computed. This is kind of a nutshell, but I'm
yeah.
helping the audience connect the dots here. But you can go back to the presentation.
Okay.
I just wanted them to know a little bit more context because some of our audience do not know anything so about machine learning. They are new and you're presenting it. So uh, at least some things I want them to remember out of this. Okay, sorry for interruption.
Yeah, thanks. Yeah, thanks. So yeah, after we import GLOM from AmazNet, yeah, I think we can create just a simple dense layer, or we call it a densely connected layer. So a dense layer consists of nodes in the input that are connected to every node in the next layer. So, we can
This is a
treat
dense
this,
network. Yeah.
this hidden layer as a dense network.
So each circle here is a neuron or perceptron, this is called, and the connections are to create dense network. You need to connect each one of the neurons in a layer to every other neuron in the layers before and after. Correct?
Yeah, yes, exactly.
Okay.
Yeah, so for the dense layer, it has the nodes in the input that are connected to every node in the next layer.
And
So
what's the number 5 there?
so the number 5 here, it's output for the current dense layer. So
How
uh,
many neurons are there? Correct? How many circles?
yes,
Okay.
so the 5 here will shows how many neurons here, and it will um, like create a dimension of 5 output.
Okay.
And yeah, in this example, you can find the output for the dense, which is -1, 5, and linear. So -1 here denotes the size of the input layer. It is not specified during initialization, but you can for MSNet, the dense layer will infer the input from infer the input units from the inputs. And for the linear here, it will fall back to like the linear activation,
It's the type
which
of neuron, basically.
yeah,
It's this computation the neural does. Okay.
yes. Usually for linear activation, it will use a sigma function like x equals to x, which is just a linear mapping from input to output.
Okay.
Yeah. So here you can also specify the shape of the input unit by calling the dense layer with in units parameter. And in addition to the in units param, you can also add an activation function to the layer using the activation parameter. So the dense layer implements the operation output equals to sigma weight times input, and then plus bias.
So stick around. You're saying for each neural unit, this is the simple function it computes. W is the weights, basically the edges, and then X is the inputs, and B is some other parameter, correct?
Yes, yes,
Okay. But it's very simple for one neuron.
yeah.
Okay.
So so for I think for most of our use cases, we will need to create neural network that more than one dense layer or with multiple types of other layers.
Okay.
Yeah, so you can find find more layers here. Yeah, this is part of MSNet documentation. You can find some like pooling or convolution or embedding these layers.
Yeah. So there are many, many options that we can use to enhance our layer to do other things other than those that you used. And this is the power of the library of MXNet. It has all of those options available for us to choose instead of us writing all of this.
Yes.
Okay.
So yeah, so how to pass the data into the network? So first, we may need to initialize the network weights. So if you use the default initialization method, which will choose the random values uniformly in the range of minus 0.7 to 0.7. So see this example when you initialize the layer and then feed into input, which has a 10 times 3 shape and randomly uniform the input feed into the layer, you can compute, get the computed output like this. So this layer will produce 10 times 5 shape output, which equals to performing computation like this. And for the parameters of the dense layer, they are all stored in a dictionary. You can access the weights and the bias by using the data method for the weights and the biases. Okay. And the next, I will introduce an sequential in MXNet.
There's some echo here.
So an
Alex,
sequential
yeah,
here.
thank you.
Okay. So for unsequential here, it will provide a special way of rapidly building networks. So when the network architecture follows a common design, which means you can stack different layers, just like a stack of pancakes. You can treat a specific layer as a pancake and then stack them into like this unsequential. And many networks will follow this pattern. So for example, we can stack 3 dense layers by specifying unsequential and call net add to stack them together. So the net, this, so the layers are ordered exactly the way you defined your neural network with index starting from 0.
So here what you're doing is that you are creating a neural network. If you switch back to the image for a second.
Yeah,
So,
sure.
so here in this network that we're showing, we have 4 input layers. Then we have the 5 neurons, and then we have 3 output layers. So basically, what
Can,
you're currently doing, you're doing something that has 3 inputs and
can
then
you
5 hidden layers, and then how many outputs? 5? Or you have only? Oh, you have 25 there.
can you zoom in just a little bit more on this?
Yeah, sure.
Thanks. Once more. There we go. That works. Thank you.
Okay.
So, and I think if I could here, if we look at the input layer, there's 4 inputs that come in there. there's then some magical, and if you just think about them as some magical mathematical functions that are going to get applied to those 4 sets of inputs, various combinations, etc. And this is by illustration. Normally in a network like this, you would have closer to 1,000 or 1,500 inputs. So you'd have a lot more lines. So they just simplified this diagram. So then you have a hidden layer that's in the middle that's going to then take all those values and combinations and put them together as you train your model. That'll come up with what computations go in there. And then that will put information into the output layer through another set of decisions that build the output layer. Then based on your values in the output layer, the machine will then make a probability guess as to the best course of action to take.
Yeah.
Is that the way information flows through this whole process, basically?
Yeah, yes, exactly.
Okay.
Okay.
Back to my question. In this example, we have 4 inputs, 5 active units, and then 3 outputs. In your neural network that you build, how many inputs you have, how many middle layers, and how many outputs do we have? Can you show back to the code? And so how many inputs do we have?
So yeah, for this example, because we have the in units of 3, so we usually have 3 inputs.
Okay.
Which means we have like for example have a matrix as the data with the shape like x times 3. So for each row of this matrix, it's an input.
Okay, so basically we have 3 inputs to a vector of 3 going into the system, correct?
Yes.
Okay, and then we have 5 hidden layer. The first dance is 5, so it's like it has 5 outputs, correct?
Yeah, actually it will map the inputs like x times 3 matrix into like x times 5. So we will get size of 5 of the outputs.
Okay, so this is the first layer, and then those 5 outputs go to another layer when they go into 25 neural units, correct?
Yes.
And then it goes out into 2 neural units. I see there's another dance here at the end. So it goes out into 2?
Yes, exactly.
So this neural network is deeper than the one you showed us, and wider, because it has more neural networks, more neural units in the middle. But also the power of this is because it created all those connections between the neural units that like you had in the figure. Am I correct here?
Yeah, yes.
Perfect. So I want to make sure that like, people understand you don't have to all of this, the diagram that you showed before, we don't have to compute it anymore. We just write this small little piece of code and it creates all of this for us. Okay, go ahead. Sorry. I want to make sure that people get it because they still don't know what the neural network does. So.
Okay, thanks. Yeah, so let's move on. So for how to like create our custom neural network. So in Gluon, every neural network layer is defined by using a base class, which is called block. So a block has one main job, which is to define a forward method and takes some input x and generates an output. So a customized block can combine multiple layers together in a single block, or also combine a bunch of other blocks together. So in this example, you will construct like 3 dense layers. The first method required for a customized block is initiate, which is used to create the layers. The other one is the forward method, which can then invoke the layers in turn to generate its output.
So a block basically can take, and whatever we did with layers, it can take many more and put them together such that you can repeat this multiple times later. Correct?
Yes.
It makes it even easier building denser things.
Yeah. So here, for the MLP, it's equivalent to stack all the dense layers into the unsequential, but we can also face some situations like we want to have a recursively called layers. So we can use an block to build up these customized neural networks.
So you don't have to use only the dense that we just learned. You can use something more sophisticated.
Yeah.
Okay.
So what about like creating the neural network with using the parameters? So for parameters, it's a method in MXNet to hold your parameters in each layer. You can create custom layers like this. So you can use a parameter class to include computation that may otherwise be not included in the built-in layers. So for example, for a dense layer, the weight and the bias will be created using the parameter method. But if you want to add additional computation to dense layer, you can create the parameter method. And yeah, so for this example, we have a simple network for the image classification. And the parameter will be declared in the constructor, and the forward function expresses the computation for model inference. So for here,
Can
we
you
can see,
explain inference before? People don't familiar with this word. It's like, what's the
yeah,
difference between training and inference?
usually for training, like what we will do is to forward propagate the inputs through this network to get like something like the loss values. So we will run the like auto differentiation to back propagate the arrows to update the weights in the neural network, so that to make sure we can have get like get a get a smaller loss in the next round of forward propagation. This is training a single step of training.
Yeah, but you're getting into the details of how it works. That's interesting, but explain to people what's the basic idea of training, and what's why it's different than inference. Like in training, what do you have? Inputs and outputs, and in inference, what do you have? Only inputs and outputs, or how does it go?
Yeah, for usually for training a neural network, you will have like a training data set, which is the inputs, and you have have like randomly initialized neural network as as your model. Then for the training, the purpose of training is to train the weights of your neural network to make sure your to make sure the neural network can apply to your training data set to make sure the loss is the smallest.
Okay, so I'll try to rephrase it. If I have data of pictures of dogs and cats, so my inputs are the pictures, My outputs are someone who told me whether this is a picture is a dog and whether this picture is a cat. And what I'm trying to do, I'm trying to train the neural network to, if I give him a certain picture, to figure out whether it's a dog or a cat. And this is the training. Am I close?
Yes, yes,
Good.
yes.
And
For inferencing, that means you have like dog or cat image, then you have already trained neural network. Then for this, the purpose of inference is to get the dog or cat with the images input.
so the difference between training and inference, if I would rephrase it, it would say, in training you know what the results are. In inference you don't know. You have only the images and you have to tell us how to classify those. Correct?
Yes.
Good. Now we can go back to this so people understand what we're doing, training, inference, and now we can go back.
Okay. Yeah. For this example, we have like a simple network for image classification. So the parameters declared in the constructor and the forward function will express the computation for the model inference. So user can like use NumPy operators from the dropping replacement of NumPy using MXNet, NP dot, and also some neural network extensions from mx.npx. So the whole definition takes just a few lines of code. So here we are just simply computing the weights times the input, and then plus with biases, and apply softmax as activation function on the intermediate outputs.
So you just written the layer, and now we're gonna train it, or we're gonna execute, or we're gonna infer with it.
Yeah, for this example, we were going to like initialize a single dense layer, and we inference on a random input with a size of 4 times 5.
So we're not training it. We're just running something. We're just saying do the computation. So
Yes,
this is an untrained neural network. This means whatever comes out is random because we didn't do any training. It's like a person who never, you asked him to do something, but they don't know what to do. So whatever they'll do is random, but at least they do something. Yes?
yes.
Okay.
Yeah, so similarly, you can use the following code to implement a famous network called LENet through block.
So now you have, I see multiple layers of different types. I see convolutional, I see pooling, I see dense. Those are types of layers, correct?
Yes, yeah, these are types of layers, and they are all stacked. Like each output of the last layer should be the input of the next layer.
Okay.
Yeah, and yeah, until now we are still using imperative programming paradigm with Gluon blocks. So it provides a user-friendly friendly way for quick prototyping and easy debugging. However, at the backend of MSNet, it can also convert the network using symbolic or declarative programming into static graphs with low-level optimizations on operators. So to make use of symbolic programming while getting the flexibility of imperative programming, MSNet provides a hybrid block. So that can run in a fully imperative way where you define their computation with real functions. But they can also capable of they are also capable of running symbolically. So let's create this is a simple example, which is a hybrid sequential, which is same as a sequential that can stack multiple dense layers. If you want to compare or optimize the hybrid sequential, you can call this hybridized method. So let's create a custom layer based on hybrid block using parameters. So this should be similar to creating a subclass of N block. So, but the only difference is that you need to define the infer shape method to let the shape of the weights to be inferred at the runtime. So this is because when you initialize your custom layer, you specify the input dimensions in units that initialize the weights with shape specified in units and out units. So if you leave this in units as unknown, you probably differ the shape to the first forward pass. So usually in MSNet, it will use the first forward pass to create the computational graph in backend. In this process, we will infer the shape. So for example, we create a custom layer with 3 out units, but we leave the in units as unknown. So when we infer the shape, we can see the shape of weights is -1, 3. This is unknown. And the x shape is 4 times 5. So we need to infer shape here. Oh, sorry. We need to infer shape here. And then when we call forward function, which means we forward computing the do some forward computation, we will get the correct input size and also the correct BIOS size. So we can evaluate the performance of hybridization and non-hybridization. So to get a sense of speed up from hybridizing, you can compare like this. Before the hybridization, we will get like 0.4 seconds to execute this neural network. But after the hybridization, it will only take 0.2.
Why is the speed up?
Yeah, because when we call hybridize, we usually in MSNet backend we usually will compare the compile the model into the graph, which is like symbolic programming did. Then when we executing the models, like when we call this network net hybrid sequencer, in Amazon backend it will call use the cached I compare the computational graph to execute on the specific inputs.
It's because basically it looks at the graph and tries to accelerate it by knowing stuff about it.
Yes.
This is why you were telling us at the beginning that the difference between the symbolic and the imperative. So
yes,
you prefer
it's
the
similar
symbolic,
to like this. Usually, we have some operators like add or fancy function. So if we call hybridize in MXNet, it will do something like what compilers will do to create
fast code.
fast pass of the computation graph.
Okay, so basically you allow it's MXNet performs like a compiler to create your neural run your neural networks, something like that.
Yes.
Okay.
Yeah. So similar to the blocks API, hybrid block is hybridized version of the block API. So you can define a forward function, and that takes an input X, and MSN will take care of the hybridizing the model at the backend, so you don't have to change your code to convert it to a symbolic paradigm. Okay, so how do we save and load MSN models? So if we want to save and load the models parameters only, you can use save parameters and use load parameters method to save the model weights. So take the simplest model layer, and as example, you can save the parameters first, then the model parameters. In this path, then you can use the load parameters to you first need to build your model, and then load the parameters onto your new model. This is such a straightforward method. And if you want to like save and load both weights and the model architecture, you can use export methods to export your model and use the imports to like consume your model artifacts.
So if you train the model, now you can just save it to file, and later, let's say when you need the model, you just load it from file and run it without need to train it again, correct?
Yes. You can also visualize your model through model summary. For example, look at the layer. You can find it has a dense this block and the activation function, and also with input. For LENet, it will has a bunch of like convolutional layers, activation layers, and dense layers. And also you can print the model architecture of the hybridized models like this. Yeah, I think that's pretty much for the
That's a good enough
suitable.
intro. We just wanted to start it, but you've done more than enough. So if anyone has
Oops.
questions that you were shy, jump in and ask them now, please. Glenn, were there any questions on the chat?
Whoops. Hold on 1 second. Okay. No, there was a couple discussions that were going on, but I think they were pretty much self-answered.
Okay.
Couple people mainly were dropping some other supporting links to other references for people that are looking for additional information.
Okay. So, do you have any questions? Any one of you have any questions about what else can MXNet can do? Because he only showed the very beginning.
I have one, and it's kind of a general one. As I'm approaching learning about neural networks, am I better focusing from a learning perspective on learning what neural networks are and kind of how they function, and then exploring libraries to do them, or learning how neural networks work by exploring the library? What would you recommend there, Jin?
Jin?
Yeah, I would recommend to learn some basic knowledge like from like theories or basic knowledges from this kind of um, deep learning textbook. Yeah, because for most of the machine learning frameworks, they will have the similar components and also the similar functionalities to help you achieve your goal.
Okay, thank you.
So, yeah.
So if you mentioned some of the other networks, machine learning libraries, so MXNet is I can say two of them, Pytorch and TensorFlow, are kind of like equivalent. Can you say something about the differences between those and why would you prefer MXNet?
Yeah, for PyTorch, I think PyTorch is based on just-in-time compiler to speed up the computation of their models. So compared to PyTorch, I think PyTorch has a large, powerful community, and I think their interfaces are more user-friendly and something like that. But I think for MXNet, it also has a large community support, active community support, and yeah, it will for MXNet also has like a huge ecosystem, including like the GLUONLP, which is used for the natural language processing uh, package, and including some natural language processing models, and for like GLONCB, which is a computer vision toolkit. So I think MSNet has a really strong ecosystem to support.
So you're saying each one of those libraries has its own advantages, and one of the advantages that you think MXNet is good at is the fact that it provides a lot of off-the-shelf extensions.
Yes.
Okay.
Yes, I think every machine learning framework has their shining points and use either like use MSNet or either Pytorch. It all depends on the like user's experience and on using their like functions or APIs.
Okay.
It all depends on the users.
So it's user preference eventually. This is what you're saying.
Yeah.
Okay. Whatever you're comfortable with. Well, Python comes battle is included for people who don't know. So here's an example. Several libraries you can choose from. Just choose whatever machine learning library you want to use and it will be good. But I saw MXNet is connected to many languages. At the beginning, you kind of talked about it. I'm not sure how much PyTorch is connected. I know it can be used by Python, but I'm not really familiar with any more extensions.
Yeah, I also want to add here is that you can see there is a fragmentation problem in most of the in the current deep learning and machine learning frameworks. So so I think for the explosion or in the current diversity of the tools that touches every aspect of the current modern day, we may need something like consortium or standards to make these packages to like standardize some APIs so that we can shallow the learning curve of most of these deep learning packages.
Yeah, this is important if you can standardize it. I totally agree.
Yeah.
It'll be easier for everyone to learn this way. However, there will always be offshoots. That's how it goes. More questions? Anyone?
Um,
Yes. Sorry, go ahead.
Oh, you had your hand first. So,
Okay, thank you. Thank you for your great presentation on Jin Zhenhui.
Yeah, thanks.
Yeah. My question is, if I understand correctly, or if I understood correctly, what you present multi-layer deep learning is at a software level, is not at, regardless what hardware we are using. The neural network deep learning is at the software level. Is that correct?
Actually, in the backend, we are considering different hardwares that our software can run on different hardwares. But yeah, in today's presentation, we are only from the angle of the software perspective. Yeah.
Mm-hmm. Thank you.
Someone else had a question.
yes. I'm curious. I may not. This may be quite an inaccurate question, but I'm trying to understand how you determine the best loss function. So I think at some point you specified that using a linear model. I think there might be other possibilities. So based on the problem you're working on, how do you know which one is best?
Oh. Sorry, I think I didn't catch up with your question. So are you asking for which loss function is most suitable for your task? Or?
Yes. So at some point, somewhere at the beginning, you specify that you're using a linear, let's say, maybe it's an activation function. I'm not sure the exact terms. Yeah, but I would.
This was activation, what he was showing. He didn't show training.
Okay.
So
Yeah.
Are there
Yeah.
different types of activation functions, and how do you pick the best depending on your problem?
Yeah. Actually, for your specific question, I think
I dropped a link. I dropped a link to a blog article on loss and loss functions for training in deep neural networks. It's a very long, detailed explanation on how to answer that question. There's not an easy answer to that question.
but Jin, you have multiple notebooks in this tutorial that you dropped in the repository. Is there something that does training that you can refer to so we can actually look in later?
yes. I actually have a notebook for training a neural network. Yeah. If you are interested, you can follow along with this. Yeah.
You can follow this and learn about more about training about loss functions. And if not, there's also documentation galore.
Yeah, I think in this book for the activation function, it's described in more details. Like yeah, some of the chapters in this book will describe something like which loss function or activation function is most suitable for some specific tasks or some specific models. Yeah.
Yeah. So it's deep. It's
Thank you.
okay. Any more questions?
I think Sherry has a question, but she doesn't have a speaker.
Yeah, Sherry also sometimes documents things. So the question is whether she's asking a question or she just documents. Does there have a question mark at the end?
Yes, but I think she was just documenting it. Yeah.
Okay.
Okay.
Sherry documents whatever is going on here for quite a bit of time now. So sometimes she asks questions, and then she says a question. So you'll see it. Anyone else questions?
Can I ask a second question?
Go ahead.
Okay. For the deep learn, for the deep training, it's regarding the training data. How much, how many training data we need to draw a reasonable conclusion. Of course, depends on how clean the data is, standard deviation. Just assuming it's complete, perfect data. What would be the, is there? I know for the quantum computer, we have like a sort of a equation. Say, okay, how many training data we need. Just calculate from that equation to see what, how many training data we need. I'm wondering for the just classical, I'm sure, well, I cannot say I'm sure, but I think for the classic or traditional computer, there should be such equation available as well, assuming it's a perfect data. How many data we'll need, just calculate from such equation.
So Jin, how much data you need to train a neural network? I think you had this question 100 times by now.
Yeah. I think it also depends. Yeah, it depends on what's the tasks, specific tasks you are working on. Depends on what kind of model you are building for.
Okay.
Yeah, for example, currently the most popular models are like the transformers in natural language processing area. So we usually train such kind of models with 10 billions or 100 billions parameters, we usually need like 10 terabytes level of training data sets. So yeah, so for such kind of large models, we probably need a lot of data sets to train.
At work, we find packages in that are delivered out of photographs. And we are constantly getting additional photos back in to continue to train. It's a continuing process. It isn't even a finite set. We're continuing to train and improve the model's accuracy to be able to find the lines and find the package in the picture. So it really depends on the amount of data you need to train a model. Really depends on what's the problem you're trying to solve. But a lot would be a good word. More than a lot would probably be a better word. And if it's a deep learning machine, it's going to keep learning. It's going to continue to keep training and adjusting itself and improve its own algorithm.
Yes, exactly. So actually, in deep learning, models and the data sets are all evolving with the times going. So for example, in 2 years ago, 3 years ago, if you train a model, the model train will not know what COVID-19 is, and will not know some like the news in today. So everything is evolving, both data sets and the models.
So, but you said something in the beginning. You said something that's like for the new neural networks that have like millions of parameters, then you need the billions. But if you have smaller neural networks, then in a nutshell, how much data do you need? Let's say I have 1,000 parameters. It's a very small neural network.
Yeah.
So how much do I need? Like how many records? 10,000 records? 5,000? 100,000?
1,000 parameters would be the parameters around about a 28 by 28 pixel piece of handwritten text that you were trying to teach a computer how to read.
Yeah.
That's just a really small little something.
Yeah. So how many records do I need? Like how much training data do I need for something like this? I'm trying to expand the answer, to expand the discussion here.
Well, it would depend on how precise you wanted the machine to be.
Well, yeah.
The more data you feed it to teach it, if you have a good algorithm, the more accurate your answer is going to be. So there isn't a finite 42. There we go. I'll use Douglas Adams said 42. Pick 42.
Is there a risk of overfitting?
You could, but you got to watch the math behind that.
What do you say about overfitting?
Well, it's just like any statistics, and you got to follow the math behind it. If you're, you don't want to overfit it also. So you want to watch your parameters. I mean, in the end, between each of these weighted values, you're really just looking at some form of a regression analysis between each node. There's just lots of them, so it's very complex.
So, Jin, can you explain? We can take this discussion off, and thank you. But are you interested in talking more about overfitting and fitting, or should we adjourn at this point and then take it offline? What do you say?
Yeah. I think I can explain a bit about overfitting.
Okay, please do.
So if a model is overfitting, which means it can perform pretty well on the training data set, which means in the data set I have dogs, I have cats. However, if you apply the model on an unknown data set that not is part of the training data set, then it could not perform really well. So it's such an abstraction of the overfitting. So which means this model works well for the current data sets, but when we validate this data set, validate this model on other data sets, it will perform worse.
Meaning it will think more cats are dogs and vice versa. But when you train the model, it told you, oh no, all the cats were correctly classified and all the dogs were correctly classified. But then when you try it in real life, oh no, it doesn't work that well. That's overfitting.
Yeah. So for example, you have a data set that includes all the corgis, which is kind of dog. Then you apply you train the model on this data set. Then you want to validate on another data set that includes all the dogs that with other breeds or types. Then I think it will not perform really well.
So what you're saying, I think the reason I asked that question is we're talking about the number of nodes, right? So the more nodes you have, I guess the more likely you're overfitting your problem. Is that right?
No.
Yeah.
It depends.
Yeah.
It depends. We're asking complex questions that are long discussions. I'm not sure Jin wants to stay all the time.
Okay.
So at this point, if it's okay, we're gonna stick around, but I do want to thank Jin for his presentation. So Jin, can you show your camera instead of stop sharing? Please show your camera so we can all thank you.
Oh, sorry.
No,
I didn't
that's
realize
okay.
that my camera is
Here we go.
off. Sorry.
Well, that's
Yeah.
okay. Now we see you. That's fine.
Okay.
So we want to thank you for your time and for showing us this MXNet. I've been looking for MXNet presentations for years, and thank you for stepping up and doing this. And I would like to thank you and everyone else. So guys, you have this button or some others, but you can clap your hands, and it's very, very
Okay.
yeah. Yeah, thank you so much. I will stop the recording now and stick around.